Hello everyone, my name is Yifan. I'm a final year PhD candidate from Northeastern University. Today in this GPU sim tutorial, I'm going to go through two topics. The first one is Dyson, a visualization framework for Akita. So one thing to highlight at this moment is that Dyson is a visualization framework for Akita rather than GPU sim. Although in this tutorial, we're only going to show how to use it for GPU sim, but if you create a new simulator with Akita, you can directly apply Dyson to your visualization tool, to your simulator, so that you can visualize what is going on in one simulation in your simulator. So let's first look at the typical simulator output we can see nowadays. When we run one simulation, we can see the simulator generally by default output some high-level performance metrics. For example, you will be able to see the total execution time, GPU kernel execution time, instruction per cycle, cache hit rate, this type of high-level performance metrics. But you typically cannot see how these metrics change over time. And it lacks of low-level details. So although you may see that in one example, in one simulation, the cache hit rate or instruction per cycle is very high or very low, it's generally very hard to make sense of why you can get this type of result. And also, the simulator knows very low level execution details. It has all the detailed information in this execution, so that if you carefully program the simulator, you can dump these low level execution traces. But in general, these low level execution traces are very large, and to simulate 1 microsecond of execution, it can generate several gigabytes of result, and can dump millions to billions of events. If you want to analyze those events by hand, you will spend a very long time, and it's very hard to find what is going on, find an interesting point to analyze. So to solve this problem, there are some performance analysis tools or visualization tools available nowadays. So let's see what type of visualization tools that are available. So first of all, we can see this is a screenshot from the Chrome browser. In a Chrome browser or any type of CPU performance analysis tools, you can see this type of flame diagram or icicle diagram. It highlights the function call relationship, so that you can see here we have one function call, then this one function calls two other functions. Then we can see how long time it takes for each function to execute. And does it take a very long time within itself, or the majority of the time is spent by calling another function? And how many functions are called in this plot is available to the user. However, this type of tools generally considers a function call relationship, which is not the case for hardware systems, and is not ideal for GPU visualization. And also, this assumes there are generally one thread that are executing, or not too many threads are executing. But in GPU simulation, there are thousands and millions of threads that are executing, and even in a general hardware execution, different components may be doing different things. So this type of visualization tools does not work for hardware simulation visualization, but it works for software visualization. So we need to consider something else. And this is a screenshot for NVVP. And there are different type of visualization tools, for example, VTune or Radian Graphics profiler. So all those tools provided by vendors typically can visualize this execution in this Gantt chart style graphs. So it captures each API, how long time each API executes, and you can see that which API execution takes the longest amount of time. But the problem of this type of tools is generally it hook up with one type of hardware that you can only apply this tool to a particular type of hardware. And also it's very high level. You can only see this type of how long time it executes for one API call. So you will see it's a millisecond level profiling result. For computer architects, we need to understand what happens in each cycle so that this type of visualization tool is not detailed enough. And finally, we have lots of tools that are available and they are designed for hardware simulators. So for example, here we can see this tool is called the ARrowViz. And ARrowViz is designed for GPU sim. And the second one is M2S Viz. It's a M2S Visual. So it's a visualization tool designed for multi-tool sim. And you can see these type of tools can visualize in really low level detail that the detail is in the cycle level. But the problem with this type of tool is that it typically visualizes a particular aspect of the execution. For example, this graph shows the execution divergence of a kernel execution, and this view shows the bank conflict on the DRAM. But the problem with this type of design is that if you want to create a new type of component in your simulation, for example, if you want to create a new cache, you need a lot of work. You need to record the traces in your simulation, and then you need to design a new view for your visualization. So for most of research, the researcher doesn't really have the resource to develop this type of visualization tool, making it really hard to visualize something that is not designed for visualization. So what we want to do in Dyson is that we have this design requirement. So first of all, we want to support visualizing parallel execution behavior so that it is good for not only GPU execution, but is useful for general hardware simulation. And we want to reveal the lowest level details so that a programmer or a user knows what exactly happens in the visualization, in the execution. And we want to keep it generic to the most of the component so that if you want to create a new component, then the visualization tool should be able to directly visualize what is happening in your new component. And finally, we care about how a software concept maps to a hardware concept. So for example, a software concept can be one instruction. So we want to see where this instruction executes, what resources it occupies, so that we can understand the software and the link between the software and hardware concepts, so that it can help us analyze the performance issues and performance bottlenecks. So as a first step, we design a data abstraction that we use a simple data structure that can capture the most of the execution details in a simulator. So first of all, we summarize everything as a task. So for example, an instruction execution is a task. So if the core needs to access the memory, then the memory access is a task. Each task has an ID field, and this ID needs to be unique throughout the whole simulation. For two simulations, there can be two tasks with the same ID, but within one simulation, the ID needs to be unique. We can identify and we can understand this task by the category field and action field. For example, this category can be an instruction or it can be a request. And we have an action field that we know what this task is doing. For example, here we are reading a memory. Now we also have this field called location so that we know which component is actually executing this task. So we assume that every task only executes in one location, in one component. If one task needs to be executed by multiple components, then we need to divide this task into smaller tasks. And also, each task has a start time and end time. Using these two fields, we know the duration that it takes for the hardware to execute this task. And finally, the user can attach any type of information in the details field, and we record this detailed field in a JSON data structure. All those tasks are organized in a tree hierarchy so that we use this parent ID to represent the ID of the parent task. In our simulation, the whole simulation is the root task where the parent ID is empty, means there's no parent task for the whole for the root task, and all other tasks are subtasks or sub-subtasks or even lower level tasks of the root task. So we create a set of APIs for users to capture this type of tasks in their simulation. So when one user develop a new component, they need to call these APIs at the proper locations in their code so that they can record this type of tasks. And the APIs is super simple. For example, if you want to start a task, you simply call this start task API. Then you provide information about this task. Then it will be recorded to either a database or to a memory or to a file. Now when this task is completed, then call this end task. Then the end time will be recorded. So we need to consider there are some special cases and common cases for tasks. For example, we have this concept called request. Say one compute unit may want to send a request to L1 cache. Then this request itself is naturally maps to a task. So we capture this type of request relationship as two tasks. One request equals to two tasks. And the first one, we have a request out task. And the start time of this request out task is the time that request is created. And it takes some time for this request to send through the network and to be buffered at the receiver side. But when this receiver component picks this request up and start to process it, we call this time required. We create another task called the request in task, and the start time is when this request is received by the receiver. And this request in task is completed when the response is ready and when the response is ready to be sent to the original sender. And this request is finalized. The request out task is finalized, is completed when the response is received by the receiver. So the whole process is completed. And what APIs we can use to capture this behavior? We can use trace request initiate when this request is created at the beginning. Now when it is received by the receiver, then we can see this trace request. We can use this trace request to receive API to capture this moment. And also, when this request is completed, when the response is ready, then we call this API called trace request complete to mark that this request in task is completed. And finally, when the sender receives the response, it can call this trace request finalize API so that we can record this request out task is completed, is finished. So only these 6 APIs, then we can capture most of the information in simulation. So here I want to show you a hands-on demo to see how we can capture this information in MGPU Sim. It's actually very easy. So here we have one simulation running. We can run one simulation. This simulation is the PageRank simulation. So by default, I can execute this PageRank by using by specifying its problem size and by setting the problem size and which GPUs we want to use. Okay, so with PageRank, we can set that we can first use -h to show us the information. Now we can see there are a few parameters that we can configure. For example, we can have this node, and we can have this sparsity configured. So let's set node to be 4K, and then the sparsity to equals to 0.001. Then let's use GPUs. Let's only use one GPU this time, and we set it to start in timing mode. Then the simulation would run, and you can see this progress bar. If we want to trace the visualization in a database, then we can run this with this extra trace with command line argument. Then this simulation will run in a trace with mode, and you can see one extra line is printed saying this trace is collected in a database, Akita trace with the simulation ID. So when this simulation starts, the simulation actually create a database in our MySQL database, and we can see that this simulation seems to run much slower, but not terribly slower than the original simulation. And we'll wait until it finishes so that we can see what we can use the traces recorded in the database and see what we can see from the visualization tool.